If you are over the age of 30, you were born at a time when we knew of just 8 planets, and they all orbited our sun. I'm purposefully ignoring Pluto. There was no direct evidence for an exoplanet or a world beyond our own solar system. But on March 21st, 2022, just 11 months ago, the scientific community crossed a remarkable threshold in finding its 5,000th exoplanet. 5,000 new worlds beyond our solar system. This is truly a landmark in space exploration. Now, for millennia, people have wondered about Earth's origin and our place in the universe. But I'm going to tell you how exoplanets open the window of opportunity for answering some of these questions. As I alluded to, the story of exoplanets on how we got from 0 to 5,000 does not actually require us to go that far back in time. In fact, the first exoplanet wasn't discovered until the early 1990s. And as of just 10 years ago, we hadn't even found 1,000. This recent boom in discovery is due in large part to 2 very famous space missions, the NASA Kepler mission and the NASA TESS mission. There are about 10 different ways that we're currently searching for exoplanets, each with their own strengths. But just 2 of them are responsible for the discovery of about 95% of the total planet population that we know of. And so they're extremely important to understand. The first of these 2 is measured by looking at the star. And as the planet orbits the star, due to the conservation of momentum, the star is said to wobble back and forth throughout the planet's orbit. This motion is measurable, and it may look something like this. These are real data on a real exoplanet system that I've worked on. And what we're seeing here is not exactly the orbit of the planet about the star, but rather the star dancing around as it wobbles due to the planet's orbit. So what we're detecting here is the speed of the star as it wobbles back and forth. This so-called wobble method is not only one of the oldest exoplanet detection techniques, but it's also one of the most highly reliable to this day. The second of these 2 very impactful and important exoplanet detection methods involves monitoring the brightness of a star over time. For most stars, the brightness is relatively constant. But if that star has a planet, and if that planet is orbiting such that it will cross in front of the star, we may notice a small dip in the brightness. These are, again, real data that I've used, taken from the NASA TESS mission. And in this case, we see that the dip in the stellar brightness is just under 1%. And so this is a very small effect. Now, as the system goes on, the planet will orbit, and it will cross in front of the star again, another dip. These data tell us that that dip, the time between those 2 dips, takes 5.5 days, meaning that a year on this planet is less than 1 week. This is 16 times smaller than that of Mercury in our own solar system. So we let the system play out a little bit further. Sure enough, the brightness in the star dips again, 5.5 days. This is a true exoplanet detection. And by studying in detail the transit events of exoplanets as they orbit stars, we can learn a lot of information. Each exoplanet method for detection has its own strengths. But these 2 that I mentioned, the wobble method and the transit method, when used in tandem, they form a powerful combination for characterizing exoplanets, namely by way of their mass, their radius, or their physical size, and their orbital period. The mass and the radius are extremely important for understanding a planet's composition. So if you imagine a scatter of all the exoplanets that we know of today, in terms of their masses and their radii, you would notice that some planets are very large, some planets are very small, and some are kind of right in the middle. But for planets with very small radii and large mass, these are going to be more dense. Conversely, planets with large radii but small mass will not be very dense at all. The density of an exoplanet is very important in inferring the planet's composition. Is it going to be more rocky like Earth, more gaseous like Saturn and Jupiter? It's often very interesting to qualify these exoplanets in terms of ones that we know in our own solar system. Some planets that we have found don't look anything at all like what we have in our own solar system. How did these planets get here? How can you come up with a planet that has so much mass but is so small? There are still many open questions to address. Another defining characteristic for an exoplanet is its orbital period, or the time it takes for a planet to make 1 revolution about its star. By knowing the orbital period, you know directly the distance that that planet orbits about its star. which is important for a couple of reasons. One of which being temperature. Planets that orbit very closely to their star are very hot. Planets that orbit very far away from their star are going to be more cold. This is a key indicator of the potential for an exoplanet's habitability. We also believe the exoplanets form in disks around young stars. By knowing the distance that a planet orbits about its star, we can infer where that planet may have formed in its solar system. And by understanding where exoplanets have formed and how their solar systems came to be, we can learn a lot about how Earth, our planets, and our solar system has formed. Thanks to a variety of detection techniques and some tremendous technology, we have built up a census of over 5,000 exoplanets, from big, large gas giants to small rocky worlds and planets comprised of lava and that have oceans. The diversity of exoplanets that we have uncovered is truly extraordinary. But we've just scratched the surface. The Milky Way galaxy is one of over 100 billion galaxies in the universe, and in it over 100 billion stars, our sun being just one of them. All 5,000 plus of the exoplanets that we've described basically are inside of this small red patch on the screen. Recent estimates show that on average, each star should have at least one planet orbiting it. So in the story of exoplanets, since we still have over 100 billion planets therefore to detect, we're still just in chapter 1. Although the field of exoplanets is still very young, we have already begun, one by one, to answer some of humanity's age-old questions. And so I encourage us all to look forward to what we'll learn from the next 5,000. Thank you.